Alrighty guys, I'm sorry that I'm not there today, but I am just not feeling very well. So for now, you're going to have to deal with um, me as a recording. So we're going to still learn and still talk about Hess's Law, which is that sixth and final method of calculating delta H that I was telling you guys about yesterday. So you guys know how to calculate it using bond enthalpies, enthalpies of formation, stoichiometry, which means moldable ratios. You know how to use the negative MC delta T, and you also know how to do one other thing, and oh, graphs. You know how to use graphs. So today you're going to learn how to do something called Hess's Law, which I've saved it for last, not because it's the most difficult, but because it helps, the stuff that you've already learned is going to help to clarify this one for you. So let's talk about what Hess's Law is. Now, sometimes it's hard to actually measure the enthalpy change for a reaction. For example, a reaction might take place too slowly, or the reaction might have an intermediate step in a series. The reaction that you're looking at might be an intermediate step in a series of reactions. Or it might occur too quickly, or many other reasons. Okay? But sometimes the thing that you're looking for, the reaction that you specifically are looking for, it's really hard to actually measure directly the enthalpy change for that reaction. And this is where Hess's law comes in. It allows scientists to measure the heat of a reaction or the enthalpy change of a reaction indirectly. So you can actually calculate that delta H without having to find a delta T or anything like that. Hess's law, or Hess's law of the heat of summation, states that if you add two or more thermochemical equations together to give a final equation, then you can also add the heats of reaction of those equations to get a final heat of reaction. So I'm going to have to pause because my dog's going bonkers. I'll be right back. Sorry about that, guys. My mom came by with chicken soup. So really what Hess's law is all about is saying that you can add two or more reactions together to get the final reaction that you're looking for. And if you're adding those reactions together to get a reaction, you should be able to add those enthalpy changes to get a final enthalpy change. So let's take a look. So, graphite is actually a more stable form of carbon than diamonds. Fortunately, the formation of diamond into graphite, so the changing diamond into graphite, takes millions and millions of years. So the question then is, what is the heat of that reaction? So we're looking for carbon solid diamond going to carbon solid graphite. Now, it takes too long to do that for us, millions and millions of years. We can't measure that. So we want to know the heat of that reaction, or the enthalpy change of that reaction. So we can do it using Hess's law and adding together different reactions. So we know that carbon graphite plus oxygen makes carbon dioxide, and that enthalpy change of that reaction is negative 393.5 kilojoules. You should recognize that number because that is also the enthalpy of formation of carbon dioxide. And that carbon diamond plus oxygen making CO2 has an enthalpy change of negative 395.4 kilojoules. Now, adding these two, if we just added these two reactions together right now, we're not going to get our final reaction. So we may need to do something like flipping the reactions around. And we've done this before using those stoichiometry and moldable ratios. So right now I've got graphite as a reactant and diamond as a reactant, but I need diamond as a reactant and graphite as a product. So if I flip the graphite equation so the graphite is a product, that means I'm also going to need to reverse the sign of my change in enthalpy. So I'm going to do that right now, and I get CO2 making carbon graphite plus oxygen gas, and now that has an enthalpy change of positive 393.5 kilojoules. Now, you might not say initially that this looks exactly like the other reactions that I'm trying to find above, but if I do some canceling out, it might work. Because if I have things just like we canceled out spectator ions in when we were doing net ionic equations, we can cancel out essentially spectator compounds and things like this, where if it occurs as a product on one side and a reactant on the other, we can cross it out. The cool thing about this is we don't necessarily have to do it in a 1-to-1 ratio. It doesn't have to be 1 mole of carbon dioxide and 1 mole of carbon dioxide on the other side. We can cancel out 1 mole with 2 moles, and you're left with 1 mole. So I'm hoping I show you examples of that. I can't remember, but there will be practice examples like that. So here I can cancel out my oxygen. I have oxygen as a reactant and oxygen as a product. I also have carbon dioxide as a product and as a reactant. Now, that doesn't change my change in enthalpies or anything like that. It's not like flipping it. But now I'm left with carbon diamond going to carbon graphite. And I need to be able to solve for that delta H. And so since these reactions are being added together to make that final reaction, all we need to do is add together the enthalpy changes of the above reactions. So negative 395.4 kilojoules plus positive 393.5 kilojoules. And I get that the reaction of carbon diamond into carbon graphite has an enthalpy change of negative 1.9 kilojoules. So you can kind of look at it like this, where you have carbon diamond plus oxygen making CO2, and that has, sorry, I was touching the screen thinking that you guys could see that. Carbon diamond going plus oxygen going to CO2, and that has a negative enthalpy change. And then the carbon dioxide going to carbon graphite plus oxygen has that positive enthalpy change. And then you're just trying to find the delta H in between. You can do that if it's easier for you guys to visibly see that. And then it's just the negative 395.4 plus the positive 393.5, and you get the same answer of negative 1.9 kilojoules. So, I would love to do another practice problem with you guys. So, let's look at what is the enthalpy change for the formation of carbon monoxide from its elements carbon and oxygen. So we're trying to look at carbon graphite plus a half O2 making CO. Okay, so that's our base equation. We're trying to find the enthalpy change of that reaction. We know that carbon graphite plus O2 makes CO2, which has a delta H equal to negative 393.5 kilojoules. We also know that carbon monoxide plus a half O2 makes CO2 as well, with an enthalpy change of negative 283 kilojoules. Now, how can we make this reaction look like our above goal reaction? And I'm hoping that a couple of you are saying in your head, if not out loud, that you need to flip one of the reactions. Right now we've got carbon monoxide as the reactant and we need it as a product. So we're going to have to flip or reverse the CO equation so that carbon monoxide is a product. And when we do that, you'll see now that we have CO2 as a reactant and CO2 as a product. So that's going to be able to equally cancel out. Okay. But we also have a half O2 as a product and 1 mole of O2 as a reactant. We can still cancel these out. They don't cancel out evenly. We're going to be able to get rid of the half mole of O2 here, but then up top, we can't get rid of a whole mole with a half mole. We can't cancel that out. So instead it becomes a half mole O2. So it kind of is like subtraction or something like that. But our carbon dioxide will cancel out evenly. And then when you rewrite that, you get carbon graphite plus a half O2 making carbon monoxide, which is exactly what we wanted. And we need to know what that delta H is. That delta H is going to now be equal to negative 393.5 plus positive 283 kilojoules. And so we get a negative 110.5 kilojoules. Okay, so we can look at that one graphically as well, where you draw out your reaction on top and what it's going to, and you have an enthalpy change, and then you know your other reaction and you're trying to solve the delta H in between. And again, it's still that same idea. Okay? So let's try another practice. What if we had 2 phosphoruses plus 5 Cl2s making 2 PCl5? Well, we've been given then these reactions. The reaction of PCl5 solid to PCl3 plus Cl2 gas has an enthalpy change of 87.9 kilojoules. We've also been given 2 phosphoruses plus 3 chlorines makes 2 phosphorus trichloride with an enthalpy change of negative 574 kilojoules. Okay? let's just look at those for a minute. Now, the thing about Hess's law is that I have to give you the equations that we're going to manipulate, because I don't expect you to know these equations and their enthalpy changes. I have to give those to you. So you won't ever be given a problem where you aren't given something to help you to solve the problem. Now, if you look at this equation, you've got 2p plus 3Cl2 making 2PCl3. Now, we want to make 2PCl5, which I have PCl5 up here as a reactant. So I'm going to need to flip that reaction to get PCl5 as a product. But I also only have 1 mole of PCl5 up here. I need to make 2 moles. So we're also going to have to multiply it by 2. If we flip it and multiply it by 2, the reaction, we're going to have to flip and multiply by 2 the enthalpy change. So we're going to have 2 PCl3 plus Cl2 making PCl5, which has an enthalpy change of negative 2 times, because we flipped it, so it's negative, and 2 because we multiplied everything by 2, 887.9 kilojoules. Okay, we can expand this and make it make a little more sense by saying 2PCl3 plus 2Cl2 making 2PCl5, which has a delta H of negative 175.8 kilojoules. And then we still have that same reaction from above. I've just written it down meter down here. Now, if you look, we can cancel out our 2 PCl3s, and then we're left with 2p plus 2 and 3 Cl2 makes that total 5 that we're looking for, and we're making 2 PCl5. So we have that reaction now. These are, again, additives, so you can add compounds together if they're on the same side. So our enthalpy change is just going to be the addition of negative 175.8 kilojoules plus negative 574 kilojoules. And that's going to be equal to negative 749.8 kilojoules. Okay? So I've got a pretty decent packet for you guys to practice. It's not a lot of work. I mean, it's enough to give you guys a good example. The reason why it looks like such a lot of work is because it takes up a lot of space to give you all those equations and all those delta H's. So it's not actually as much work as you're going to panic and think it is. But you should practice that. I'm going to have, I should have the answer key out on the lab bench. You guys know what to do with that if you need it. And then hopefully I'll be able to be in school on Wednesday. So I hope that you guys are nice to the sub and have help each other out. If you're not understanding something, go and ask a neighbor who seems like they're rattling through and having a good time with it. So please work together and help each other out, and I'll see you soon. Thanks so much, guys.